So you've seen an example of a differential equation before. So this is an equation between some unknown function and one or more of its derivatives. So maybe something like this. Now we're going to be looking at the same thing, but since if we change from f being a function of a single variable to f being a function of several variables, then we might have something where we have an equation between different partial derivatives of x. So that's what's meant by a partial differential equation, or PDE. And these are extremely useful because they can model all sorts of natural phenomena. So we'll look at a couple of examples. So the first one is called the wave equation. So this is a one-dimensional wave equation. This is used to model waves traveling through a string. So we will take u as a function of x and t to be the displacement of a string at location x and at time t. Okay, so the idea here is that if we have some, say we have a little interval, so here's the interval from 0 to L, so this is a string of length L, and if we take a time snapshot of it, maybe at time 0, we have some curve that looks like this. So this is the graph, this is u of x at time 0. And then maybe if we wait a second and the wave has traveled along, then we have something that looks more like this. And so that's the graph of u at x1. And then either further in time, it's come down to here, and that's ux2, and so on and so forth. So these are just different time slices of this particular function. And if we were to arrange them with the time axis going down the side, so like this, okay? So now we've got the x-axis going this way, and we've got time axis going into the future that way. Then you can see the solution of this equation actually traces out some sort of surface with a bump, something like that. Anyway, that's beside the point. Right now, we're not going to worry about the particulars or how this is derived or anything else, but I'm just going to flat out tell you that this u, for physical reasons, has to satisfy that the second derivative of u with respect to time is equal to some constant, some positive constant, so I'll call it a squared, times the second derivative of u with respect to the spatial variable x. And so in this equation here, a is propagation speed. So in other words, it's how fast the wave is traveling. And this depends on various things like tension on the string and density of the string and stuff like that. Okay, so it's how quickly the vibration moves along. And so it's interesting to note that on the left side here, the second time derivative of something is acceleration. The second space derivative of something is curvature. So this is telling us that there's a relation between acceleration and curvature. And so, for instance, where the curvature of the function is big, so if I look at the blue one right here, that means that that's where the acceleration is greatest, and the acceleration is going to be in the vertical direction only, because we're looking at just a one-dimensional wave. So that's where it's going to be accelerating the most. Over here, the blue one is flat, and so there's no acceleration whatsoever. Anyway, okay, so that's just a way of looking at the difference between the time and space variables. So leaving that aside, we're not going to worry about where that equation comes from and try and solve it, but I'm going to say, how do you verify that a given function is a solution? So if we take cosine of x minus at, verify that this is a solution. And it should sort of make sense that this is a solution, because if we look at ux0, ux1, and ux2, what do we see? Well, basically something just like the picture I drew in the outset. The wave is going to be shifted to the side by a times whatever number appears here, because that's exactly what this says. This says we're going to take cosine of x and we're going to shift it by a to the right, or sorry, by a times t to the right. Okay, so to verify that it's a solution, however, all we need to do is check that uxx equals utt, with an a squared there. Okay, so taking the first partial of u with respect to, let's do t first because that's how I wrote it originally. With respect to t, the derivative of cosine is minus sine. And then we have the inner derivative with respect to t, so we differentiate this thing and we get a copy of minus a. Then if we differentiate this thing with respect to t again, then we will get minus cosine again, and we will get another copy of minus a kicked out. So this will give us minus a squared cosine x minus at. And if we look at the spatial derivative, the first derivative is, let's see, so we're going to do, so we'll get minus sine x minus at. And then the second space derivative will give us minus cosine x minus at. And so if I take a squared times this second spatial derivative, then I get minus a squared cosine x minus at, and that is indeed equal to the thing that I found for the second derivative with respect to time. And so since these match up down here at the end, we have verified that this is in fact a solution of the differential equation.